Hello, so welcome to part 2 of Blender for Physics. Part 1 seemed to go down relatively well. It has a few hundred views, which is not too bad. So a lot of people were asking me about how you can import data from outside Blender and use it to make 3D models. So if you follow me on Twitter, you'll have seen that I've been posting images of DNA, chemically accurate DNA, which were made in Blender. And those images were made simply by importing geometric information about molecules from PubChem into Blender using some simple pieces of Python code, and then building it using Blender's inbuilt Python package. And that's what I'm going to cover. That's what I'm going to cover here. I'm going to split this into 3 parts because it's quite a long project. So in part 1, we're going to look at how to convert external chemical data into a format that can be read by Blender, how to then build a molecule based on that imported information, and how to make that molecule look presentable. In part 2, we'll then look at how to actually build the structure of something as complex as DNA, and how to manipulate it in Blender using some of the more advanced 3D modeling tools. And then in part 3, I'm going to show you how to use the compositor to make images made in Blender look really, really good. Okay, so that's how it's going to break down. Okay, so for the first part, which is obtaining external data and importing it into Blender, you're going to need Python installed, and you'll need to install another package called OpenBabel. Okay, so everything I'm going to be showing you in this part of the tutorial is based on this post from Patrick Fuller. So Patrick Fuller wrote or collaborated on, I'm not sure if he's the sole author, of a piece of software called OpenBabel. And basically what this is, it's a way of communicating between different types of chemical information files. So there's a huge variety of different methods for describing and storing molecular information and chemical information in different file formats to be read by different programs, and OpenBabel is a way of translating between these different formats so that there's some degree of universality to this data. It's all a bit of a minefield, to be honest, but OpenBabel is a powerful tool helping to clear that minefield. And within OpenBabel is a Python package called Pybel, which we're going to use to write some code that can take simple strings of chemical information and convert them into geometric information. And the first thing that you're going to need to do for this is to download and install OpenBabel. Now, the reason why there was a bit of a delay in getting this episode of the tutorial up is because I've had huge problems with running Pybel and OpenBabel. So I primarily work in Anaconda when I'm using Python, and there seem to be a few problems with OpenBabel in Anaconda, but I think they're solved now. So the first thing that you should do is download and install the latest version of OpenBabel. You can do that by going to the OpenBabel project in GitHub, and you can compile the project from there if you so wish. But if you're working in Anaconda, a much simpler way is just to do a conda install using conda forge. So type conda install -c conda forge OpenBabel. And this won't run a proper install because I already have it installed, but that's what you run. If you work in a different Python environment, you can do a pip install of OpenBabel as well. I think that works. There are a couple of different ways of doing it. But if you are having huge problems installing OpenBabel, which I was, I've also created a Blender for Physics Git, so you can get all of the files that we're going to generate in JavaScript format from here, and you can just ignore the whole OpenBabel part of this. So if you're stuck on the OpenBabel installation, don't worry, just go to the Git and download these files, and you should be able to run everything. And I've also uploaded all of the Python code and the code for Blender that we're going to use in this project. Okay, so once OpenBabel is installed, go to your preferred IDE. I like to use Spider because, I don't know, I'm old. And then, for some reason I don't like using Jupyter. It's great. I don't know why. I'm just resistant to new things. It's very new. So make a new project. And what we want to do now is we're going to write some code using the Pybel package in OpenBabel, which is going to allow us to translate a chemical information file, a crystallographic information file, or various other formats into JavaScript object notation, which is a generalized data format that we can then import into Python and easily read in order to construct our molecule. Okay, so the first thing that you're going to want to do is import OpenBabel. And from OpenBabel, you want to import the Pybel package. Okay, and we also need to import JSON, JavaScript object notation. That's going to allow us to convert this chemical information into JavaScript. Okay, so check I'm still recording. This is the second time I've done this tutorial because after recording nearly 2 hours worth of material that I was going to trim down into this tutorial, OBS crashed and so did Blender and all my files were corrupted, so hope this sounds like I'm doing it for the first time. Okay, now we want to create a molecule object, and we're going to read, using Pybel, a string which represents the molecule that we're going to create in Blender. We can do this in a couple of ways. We could read it in as a string. We could also read a file. So we could read CIF files. We can read mol files. But I like the idea, personally, of building an entire molecule just from a string that can be copied from almost anywhere on the internet. There's something really appealing. There's something really appealing about the idea of just putting in a chemical string and turning that into a 3D molecule. And we're going to use Smiles notation, which is one of the most common ways that chemical information is represented. You can also use Inchy, and in fact we're probably going to use Inchy in this project because I think one of the molecules we're going to import throws an error if you try to compile it from Smiles notation. But we denote the smile format just by putting SMI in the format field. And now we actually need to enter the string that contains the chemical information. So for this, what you need to do is you need to go to PubChem. PubChem is a repository that contains vast amounts of information about all sorts of different chemicals. And because we're going to try and build this DNA project, which I posted on Twitter, the first thing that we need to do is get hold of the backbone for the DNA molecule, which is the deoxyribose phosphate group. Okay, so if you type deoxyribose into the search field in PubChem, you should find this molecule. Okay, so this is the basic unit of the DNA backbone. And in PubChem, you have a lot of different information about this molecule, including 3D models. Okay, which they don't look as good as the one we're going to make in Blender. Oh no, but they do exist. And you can download these 3D models in a bunch of different file formats, including JSON, which is what we're generating. Now, you might think, why not just download the JSON file from here? Well, this file is in a different format to what we're going to create. You can absolutely download this JSON file and you can import this straight into Blender, and you can write a program that parses this and turns it into Blender objects. But you won't be able to download this file and turn it into Blender objects using the code we're going to write in this tutorial, because this has a different structure. Okay, but hopefully through this tutorial, you'll learn enough about how to use Blender's inbuilt Python functionality that you could write a custom script to interpret this file. But what we're interested in this case is the canonical smiles notation at section 3.14. So in order to create our molecule, just copy this string, go back to your code and import that. There we go. Okay, now that string, that contains all of the atoms that are in the molecule, and it contains all of the information about which bonds exist between different atoms, but there's no actual 3D vector information in there that tells us about the geometry. So in order to make that string into a 3D molecule, we're going to use a PyBall functionality called make3D. So if we type molecule.make3D, what that's going to do is it's going to take that string and it's going to compare it to a library of molecules that's downloaded as part of OpenBabel called rigid fragments txt, which you'll find in your OpenBabel library. And that contains hundreds of reference molecules and geometric information that tells PyBall what the bond angles and positions are for certain atom groups. So when we run make3D, it's going to use that library to calculate the positions of all of the atoms in the string that we've just entered. Okay? Right, so now we've got our molecule and we've made it into a 3D object in Python. So what we need to do now is convert that molecule into the JavaScript object notation format so that we can import it into Blender. So for this, we're going to create a new function called molecule to JSON, and we're going to pass this the molecule, the 3D molecule object. Okay, so the first thing that we need to do is create a array of all of the atoms in the molecule. And this is going to contain information about the elements, elements, there we go, element. And that information is stored in the 3D molecule as atom.type. And then we need the actual location in space of those atoms, and that is stored as atom.coords. Okay, and then we need to iterate this over all the atoms in the molecule. And I'm going to move that curly brace because I always put that curly brace in the wrong place. There we go. Right, so we're going to do this for all of the atoms in our molecule object. Okay, right. So now we have all of the atoms, the elements, and the locations in a list. Array? List. One of the others. I can never remember the difference. I know, that's ridiculous, but I can't. I'm going to cut that. Right, okay, but now what we need to do is look at the bonds. Now this is slightly trickier because the 3D molecule object that we've created in Python, it contains information about which atoms are bonded to other atoms, but it doesn't contain separate bond objects. So we need to generate those. So we're going to define our bonds array, and we are going to put into this the individual atoms. So there are going to be two atoms in a bond, the start atom and the end atom. Okay, so we're going to obtain these by saying from B, which is a bond, get begin atom, and we're going to record that atom as an index, which will be either 0 or, as an index which tells us which atom in the molecule it is. So every atom in the molecule is going to be assigned a number, and then we can refer to which atom which atoms the bond is between, just based on those numbers. Okay, so that's get begin atom, and then we do the same for the end atom. Get index. Okay. That's in the wrong place, yes. And the other piece of information we need is the order of the bond. Okay, so a bond can be single, double, triple, etc. And we need to know which one of those it is. So we have field order, and for that we get bond order. And now curly brace? Yes, now curly brace. Okay, and again, we're going to iterate that over all the bonds in the molecule. So we're going to say for B in, but we're not just going to say for B in molecule.bond, because there is no bond attribute for the molecule. So we have to generate the bond information. So we're going to do that using an OpenBabel, sorry about my typing. We're going to use that using a function in OpenBabel, which is the OB bond builder. OpenBabel. What's going on? There we go. Right, so OB mol bond iter. So this is iterating over all the bonds in the OB builder, and we're going to pass this the molecule object. OB-mol. Okay, right. So now we have an array which stores all of the atom's elements and geometric locations and all of the bonds, and each bond is recorded as the index of the start atom, the index of the end atom, and the order of the bond, whether it's single, double, or triple, or higher, potentially. And now we want to store this as a JSON file, so return JSON dump atoms and bonds. Excellent. And now we need to actually save this file. So we can call this ribose for now. I know it's deoxyribose and it means something different, but you know, I'm not a chemist or a biologist. I'm just a dumb physicist, and I don't know the difference. And we're writing to this file as out file. Okay, so that's giving us the file name and type, and now we're actually going to pass our molecule into this file using the molecule to JSON function that we just defined. There we go. Okay, so let's save this script. Let's call it SMI to JSON. JSON sort of sounds like someone misunderstanding Friday the 13th. JSON. Right. Let's run this and see if it works. Molecule.atom. That's okay, isn't it? Molecule has an atom type. Oh, atoms. That's why. There we go. Okay. Name OpenBabel, not OpenBabel. Where's that? Line 12. There we go. That should be get begin atom, not atoms. Fine. Okay, right, that's run. So now if we navigate to the correct file, correct folder, we should find a ribose file, JSON file. And here you can see the format of this. Okay, so we have, let me check I'm still recording. I'm so paranoid about that now because I lost 2 hours. Okay, there we go. Right, so what we have our atoms field, and then we have a list of every atom in this molecule. So we have element, and then we have an element recorded, along with the number of bonds that this atom has, which will become important later, and then a location as a 3 vector. Okay, and then if we scroll to the end of this file, here, we have a bonds field, and then we have all the bonding, and you can see here we have the atoms involved in the bond, which are identified by 2 indices, and then an order field, which is just an integer telling us whether it's first, second, third, etc. order. Okay, so that is now our JSON file that we can import into Blender and start building our DNA from. So next thing that you need to do is open up Blender and start a new project. Okay, click off this to get rid of the panel. And now we have our scene. We're not going to use any of the objects in here, so just select them all and hit delete to clear the scene. Now we're actually not going to be doing anything in the 3D viewport. In the last basic introduction tutorial, we did everything in the 3D viewport using Control-A and importing different objects. We're not going to do that because we're going to do it all using Python. So go to the top bar and you'll see at the end you have a scripting window. So click on that to go into scripting. And what you'll find is you now have your 3D viewport in the top left here. You have a console, a system console that you can see underneath this. You have whatever that would be called, a output, I guess. And we have a text editor in the middle. And then on the right here, we have our collections, just like we do in the standard scene view. And then we have a very useful drop-down menu here. This is a breakout of the data file associated with this Blender project. So this contains all of the individual data groups that exist within this project. And then at the bottom, we have our properties menu, again, just as we would in the scene view. Right, so to start off, we're going to create a new text file. Okie dokie. Now, Blender has an inbuilt Python module called BPY, or Blender Python, and that contains sets of commands that you can use to generate and manipulate objects in Blender. Now, it's not quite that you are running Blender and communicating between Blender and Python with whatever environment you're running Python in. It's more that there is a Python environment built into Blender. And that's important because it means that there are some packages which might not be compatible with the Python environment in Blender. And the big problem I've had is trying to use NumPy in Blender, which is really irritating because NumPy is like one of those quality of life packages, which is just like absolutely vital. But I've had huge problems running it. If you import NumPy and it works, that's really cool. And please, if you did something to make that work, tell me. If it just works for you, then also tell me, because I'm interested in figuring out what's going on and why I can't use it. So a lot of the things I'm going to do, you might think immediately, oh, I can do that in NumPy, and it's way easier, and you could do it this way. I know. I know that. But I can't run it. Okay, so we're going to do it without. Okay, so the first thing that we need to do is import BPY. And I don't understand why we have to import BPY, because it says right here that it's a built-in module, so I don't know why we're having to import it again, but we do, and if I don't do that, it throws an error. And we need to import JSON as well. And then, because we can't use NumPy, we're going to use a different maths mod called mathutils, and from that we're going to import vector notation. If I could type, it would save me so much time. One of my friends is a software developer, and the first month that he was in the job was entirely devoted to him learning to touch type, and he said it's absolutely saved his life. But I can't touch type, and I make lots of spelling mistakes, so sorry about that, but you know, we'll get there eventually. Right, so we've now imported the relevant packages. So what we need to do now is we need to define a function which is going to turn that JSON file that we made into geometric data and Blender objects so that we can draw it into the scene. Okay, so we're going to define a new function called draw. Define a new function called draw molecule, and we're going to give this an argument molecule. Okay, so what we're going to do here is read through the atoms field in that JSON file and turn every atom into a sphere object in Blender. So for atom in molecule atoms, for, not fro. So for each one, we're going to create a new UV sphere object. So the command you need for this is bpy ops, which is operations, mesh, primitive, UV, sphere, add. Okay, and this has a number of different fields. The ones we're going to use are scale. Okay, so for now, just put 1 in. The blog post I showed you before, the Patrick Fuller one, the Patrick Fuller blog post that I showed you earlier, there's code in there which mirrors a lot of what I'm doing, but that code is for a much older version of Blender. And a lot of things have changed since then, and this is one of the things that has changed. So it used to be that you could define any object in Blender using a single size, and that would just scale it according to its default dimensions, and you can't do that anymore. For some reason now you have to do it by scale, not size, and in the last tutorial I explained the difference. But also you have to enter X, Y, and Z scales, and I don't really understand why, but it seems that you do. So we have to enter this as a 3 vector. Okay, so we want to import it with a scale of 1, and then we want to use the location information from our molecule file. So for each atom, we're making the location of the sphere that we're generating equal to the location field in the location field for that atom. Mr. Dot there. Between mesh and primitive, there we go. Okay, and then because we don't want it to look like garbage, we're going to use a command that sets this object to shade smooth. Okay, so that will import each atom and turn it into an object in Blender. So now we just need to read in the file and pass it into this function. So we're going to say with open, and then we need the file path for the deoxyribose file that we just created. For me, it's in my D drive, but it will be in wherever you generated it. So it's there. .json. And we're importing that as an in file, and then we are passing that file to the molecule objects, and then we're calling the draw molecule function, giving it the molecule. Okay, and that should now draw us the molecule that we want. Now I'm just going to save this quickly, because one of the other things that happened when OBS crashed is that it also crashed Blender, and I lost all of the code that I made for this tutorial. So I'm now doing this kind of blind. Okay, right, so if we run this, we get an error. Okay, right. So if you want to look at the system console, go to the window drop-down menu and click toggle system console. And what am I getting? Import mathutils. Oh, that should be from mathutils import vector. That's why. There we go. I really should just Control S. I should get used to doing that. Okay, there we go. Right, so now we have our molecule being imported. If I go back to layout, the layout tab at the top here, you can see it in the 3D viewfinder. Okay, so we have atoms that are appearing, and they look kind of molecule-y, but it's a bit rubbish. They're all the same size. They're all blurred together. This is not what we want. Okay, so we need to elaborate on this. Now, the main thing that we're going to need to do is be able to distinguish between the different atoms in the molecule so we can give it color. You know, we don't want to just be going through and like looking up in a table, oh, this one's a hydrogen, this one's a carbon. That's incredibly boring. We want to do that with the code. So, what we want to do is read in the element information from our JSON file. Still recording, good. Read in the element information from our JSON file, and then what we're going to do is create materials and assign them to each element. Okay, so for this, what we're going to do is in the point where we're reading in the atoms, we're going to say that if atom element in BPY data materials keys. What that's saying is right. What that is saying is if the element field for the atom is in the materials index, not materials, if it's in the materials index list, then do something. So the materials index list is over here. Okay, this is the breakdown of the Blender data file, and you'll see here that there's a drop-down called materials, and this lists all of the materials that exist in this Blender project. Right, so what it's going to do is it's going to take the element associated with that atom and look for a material in here that's been assigned to that element. And if it doesn't find it, if it does find it, we can do one thing. If it doesn't, we can do another. Now we could run this, and we would look for materials according to element. But if you look in the ribose JSON file, you'll notice that the elements are not just denoted by their chemical symbols, they also have a bonding order associated with them. So we have C3, O3, etc. So it's only the first character of the element that we actually want. So we're just going to put next to this 0, and that will read just the first character of the element field. And that will prevent us from doubling up. So if we have O1, O3, and O2, we won't double up on our materials. So if there's a material in the Blender data file that matches the element, then we just want to assign that material to the UV sphere object that we've created. So we're going to take this part here, which creates the UV sphere. We'll put that ahead of this because we're assigning the material to an object that already exists. So then in this field, we're going to type, I have a reference over here so that I don't make too many horrendous mistakes. What am I doing? So from BPY, we're doing, right, so from BPY, we're going to use the context commands. So this is the same as using a context menu through the normal route if we were in the 3D viewport. We're looking at the active object, so that's the selected object, which, because we've just generated a UV sphere, by default, the sphere that we've generated will be the active object. And then in the data field for that object, we're looking at the materials that are assigned to that object, and we're appending to those materials the material which matches this object's element. Element. E-L-E-M-E-N-T. element. Right. There we go. What if it's not there? Okay, so if there is no material assigned to this element, we need to make one. So then we're going to say bpy data. 1 second. Yes. So in the data class, we're going to make a new material, materials.new, and we're going to assign that material a key which is equal to the first character of the element field for this atom. Okay, and then we're going to assign the material that we've just created to that object. Control S to save. Right, okay, so we already have these objects in here. We don't want to be rendering objects on top of objects, so remember to clear the scene each time. So just select everything in here and delete. Alternatively, you could go to collections in here and delete the objects directly from the data menu. Okay, so let's run this. Oh, what a surprise! It threw an error. What was it this time? Invalid syntax on line 13. Oh, forgot my colon. Run that. Okay, right, so now we have a molecule. Let's go back into the layout tab so we can see it a bit more clearly. Okay, so if I, in my properties menu on the right hand side of the screen here, if I go down to materials, I can see that now each sphere has an element assigned to it, H, O, H, O, P, etc. Okay, and then, sorry, what I can do is from this material that's assigned to it, I can click on the base color, and I can change its color here. And if I do that for, say, hydrogen, then all of the hydrogens in the system will change color. Okay, so that is much better, but this still looks rubbish. So there's a couple of things that I need to change. One thing I don't like is that every atom here is just called sphere. So that makes it really hard to tell what which atom is which. So what I'm going to do here is I'm going to assign a name to each sphere that's just its element. Okay, so I'm going to say bpy okay, sorry about that. It took me a little bit of time to figure out where the difference falls between the context command group and the data command group. So what you need to write is bpy.context.object.name, and then the element component of the atom field from the JSON file. So if we run this now, we can now see that each atom gets a name that refers to its element. So all the oxygen atoms are called O, phosphorus is P, hydrogen is H, etc. Okay, great. So we're getting closer now. So we now have materials assigned to each object, and we can see as well that if we delete this molecule and we run this script again, we retain the same materials. So that means that you only ever need to run this script and generate materials once. And then if you put in new molecules and you generate them using the same script, they'll inherit the materials from the previous iteration. Okay, so that's quite useful. You don't have to change your materials every time you import something new. But there's another problem here, because all of these atoms in the molecule, still recording? Yes, good. All of these atoms in the molecule, they're all the same size. And the hydrogen atoms shouldn't be the same size as the phosphorus atoms or the oxygen atoms. Okay, so we want to change their radii in deference to their element. So for this, we're going to create a list of radii, and we could potentially put in a list for every element in the periodic table if we really wanted to, but I'm just going to do it for the materials that have shown up in this list. Okay, so what's first? Carbon. So I'm going to enter the atomic radius in picometers, which I've got from Wikipedia here. So nitrogen, 71. Why am I putting nitrogen? Oh, that's from later in the project. That's why I've got that in my list. Hydrogen is next on our list. So hydrogen is 31. What else? Oxygen. Oxygen is 66. And phosphorus. Phosphorus is 107. Okay, so that's my list of radii, and that's in picometers. If I were to put these radii into my project, it would turn them into meters, and all of these would be enormous. So I want to normalize them. So I'm going to say for key in radii.keys. Radii. Oh, I always forget my. So I normally program in C# most of the time, and I've only started using Python like daily this year. Well, last year, 2020. So I'm still dropping tabs and colons and semicolons all over the place. So please forgive me for that. So for radii key, we're going to normalize this. And I'm going to multiply it by 0.4, and I'm going to divide it by the radius of hydrogen, so that hydrogen acts as my sort of reference atom. Okay, right, and then when I generate my UV sphere, I want to assign this radius to the scale. So what I'm going to do in here is I'm going to do a check to make sure that the atom that I'm generating is in my list of radii. So I'm going to say if atom element 0, so just the first letter. Did I specify that? Yes, I did. I'm pretty sure I did. Is in BPY data. Is in radii dot keys. So if my element is in my list of radii, then I'm going to have a variable s, which is going to be the radii for this atom. Those shouldn't be curly braces, they should be square braces. Element 0. Yes. So it will assign it that scale, and if it's not in my list, then I'm going to assign it something ridiculous. Okay, so it's going to be way too big, and I'll know that something is wrong. Maybe even more than that. Okay, so that I'll know that I've obviously missed something, and then I could just click on the atom, and I can look at what name it has, and then I'll know which element I've missed in my radius list. Okay, right, so let's delete that. Oh, and in here, in scale, I need to actually enter my variable s. Quick save, Control S, and now run. Perfect, that looks great. So now all of the atoms are different sizes. The hydrogens are small, carbon and oxygen, similar sizes, and the phosphorus is a bit bigger, which is perfect. Okay, I'm going to go into layout quickly. So I now have something that looks more like a molecule, but there's something obviously missing because we spent a lot of time in the stage where we were writing the Python program. We spent some time converting the molecule information to list the bonds so that we could draw a ball and stick model, and there are no bonds here. So we need to draw the bonds. Right, so let's go back to scripting. So we have our thing for generating atoms. Now let's make one for generating bonds. So for bond in molecule bonds. So if we go back to our ribose file, we see that each bond is listed as a starting atom and an end atom and an order. So what we need to do is pull out the atom index, compare it to the locations of those atoms from the atom list, and then turn those two locations into a vector that tells us where the bond is going from and to. So we're going to say first first location is molecule, atoms, bond, atoms, 0. So only atoms that are first in the list, so the starting atoms. Location. I've missed a square brace somewhere. Molecule, atoms, that one's closed. Ah, there it is. There. Location. So that's going to pull out the position in space of the atom that begins this bond. And then second location is molecule, atoms. Why am I typing this? Copy and paste is the thing that exists still. There we go. And all I need to do then is change that from 0 to 1. So I'm now looking at the second atom in that set of indices, which is the ending atom. Okay, so now I've got the location of the atom that corresponds to the start and end of the bond, and now I'm going to create a tuple which is going to describe the vector between the starting and ending atoms. So I'm going to say difference is tuple C2 minus C1, so those are just two arbitrary indices that describe the start and end position for C2 and C1 in the zip of first location and second location. And another bracket. So what I'm doing, I'm taking these two locations, I'm passing them into this zip, and then I'm reading them so that I take the difference between these two positions and turn that into this tuple. Okay, and then center. So we've now described the vector between atom 1 and atom 2. Now we need to describe where that bond actually is in space, where its center point is. Okay, so this is going to be another tuple, and this is going to be C2 plus C1 divided by 2, which will give us the middle position between those that starting and end point for C2 and C1 in that same zip. I can just copy this again. Okay, right, so now we have the vector and the center of the vector, so now we just need its length. So for that we're going to take magnitude, and that's going to be the power. So for the magnitude we want the root mean square of these two vectors, so we're going to say power of the sum of C2 minus C1 squared for C1, C2 in zip, and this is the same zip as before. The only difference is that in the power we're going to raise this to 0.5 because we're taking the root of the mean of the square. Right, so now we have these three vectors that describe which direction the bond is in, where it is in space, and how long it is. So now what we need to do is take that vector information and turn it into a rotation. So when we create this bond as an object in Blender, it's going to be oriented vertically along the z-axis. Okay, so we need to compare that orientation to the orientation that we want it in and turn that into a set of Euler rotations that are going to turn it so it's pointing the right way. Now we could do this by calculating Euler rotations in x and y and z and then inputting those into a Euler rotation command, which is sort of what Patrick Fuller did in the original code that I've used as a base for this. But it's actually much easier to do that by converting everything into quaternions. So that's what we're going to do. So we're going to define a vector called v-axis, which is going to be that differential vector, so the vector going from bond 1 to bond 2. And we're going to normalize, is it Z or S? It's American English, so it's Z. We're going to normalize that. And then we're going to define another vector called vObject, and that's going to be the vector that this cylinder object will originally be oriented along, which will always be the z-axis in Blender. Okay, so we're going to take those two vectors, and then what we're going to do is generate our object and then turn those vectors into quaternions and perform a quaternion rotation. So first of all, we need to generate our object. So BPY OPS mesh, and same as before, primitive, but this time it's a cylinder. Add radius. So the radius of the cylinder, you can make that anything that you like. I'm going to make it 0.1. And then the length of the cylinder is recorded as depth. That's the magnitude, which we calculated before. And then we need to position this in space. So we're going to say its location is at the position center. Okay, and as before, we don't want it to look rubbish. So we're going to set it to shade smooth. Okay. Right, now the slightly tricky bit. So what we're going to do here is we're going to take the object and from the context menu, we're going to change its rotation mode into quaternions. So we're going to say BPY context object rotation mode is quaternion. Okay, and now we're going to apply the quaternion rotation. So BPY context object rotation underscore quaternion equals v-axis. So that's this axis, the normalized differential between the two atoms, to track quaternion z y. Okay, so what that's going to do is it's going to apply a quaternion, it's going to use the quaternion to calculate a rotation in x and y, and then it's going to apply that as a Euler rotation to the object so that its principal axis, its z-axis, is oriented along the tuple which defines this vector diff. Okay, right, so now if we run this, we should generate the bonds, calculate the correct orientation for them, and then apply that orientation. So let's delete what we have in the scene, and let's run this script. Oh, gosh. Okay, right. Error. So we have created a bond, but it hasn't rotated. Why? Line 45. None type object has no attribute to track quad. Ah, okay. Right, I found the problem. It's because I said normalize. That should be normalized. So it wasn't recording the v-axis as a normalized vector. So that's the problem. Okay, clear the scene and try again. Hooray! Right, okay, so now you can see that we have bonds that are covering the distance from one atom to the next, and they're all correctly oriented in space. Okay, so we're getting much closer to the correct picture that we want for our deoxyribose molecule. But there's still a problem because I happen to know that some of these bonds should be double bonds. This one, for example, here, this oxygen bond between the oxygen and the phosphorus, that should be a double bond. That's why that oxygen doesn't have a hydrogen atom on it. Okay, so we know if we go back to our ribose file that we recorded the order of each bond and whether it was first, second, or third order. So now we need to create some code that's going to define that and give that information to our drawing program. So we want to check for each bond what its order is. So we're going to say if bond order is equal to 1, then we're going to create a translation vector based on the order of the bond. Okay, so in this case, the bond order is 1, so there's only one bond. So we want the translation vector to be 0 in 3 dimensions. Okay. If it's not 1, if instead the bond order is 2, in this case, our translation vector is going to be the bond radius, which I think I put earlier as 0.1. Yes, I did. If I was not being completely horribly lazy, then I would define the radius somewhere else. But I am completely horribly lazy, so I'm doing it in this terrible way. So I'm saying 0.1 times x for x in the object. So what I'm doing here is I'm taking the v object vector, so where it's originally generated, where I create my cylinder that's oriented along the z-axis, and I'm saying for the x dimension of that cylinder, move the second cylinder 1 times the radius in that direction. Okay, so I'm now creating 2 cylinders that are separated in space, and then I'm rotating them as a pair. Okay, so I'm taking those 2 and separating them, and that's for 1. So the other cylinder, if this is a double bond, needs to be moved by the radius in the opposite direction. Okay, so they're starting in the same place and then they're moving like that. Okay, so it's minus 0.1 times x for x in the object. Okay, and in the case that this was a third order bond, which I don't think there are any here, but just to be on the safe side, if this was a third order bond, then we would want to move these double that distance apart, and we would have another bond in the middle, which we aren't moving. Okay, so then for these translation vectors, what I now want to do is I want to generate a cylinder for each translation vector. So in the case of a single order bond, I just have 1 translation vector, so I'm making 1 cylinder. In the case of a second order bond, I have 2 translation vectors, so I'm creating 2. Have I missed a square brace here? Yes, maybe? Yeah, I think there needs to be a square brace there. And then an extra one there. Is that the case here as well? Yes, there and there. Sorry about that. Okay, so then for the third order bond, I have 1, 2, 3 translation vectors, so I want to create 3 cylinders. So I'm going to create a new loop for tran in trans, for, not fro. So take this script that creates the cylinder and rotates it and put it inside this loop. Okay, and then at the end of this, I'm going to add my translation vector. So I'm going to say bpy ops transform translate. So that's a spatial translation rather than a rotation. Value equals tran. Okay, give that a quick save. Check I'm still recording. Yes, good. Okay, and now let's clear the scene and run this file. Oh, what a surprise! An error. Line 49, fortran in trans. Invalid syntax. Really? Oh, ugh. Told you. Terrible in Python. Okay, nearly there. What's wrong this time? Translate error. Could not be found. Probably means I've misspelled something. There we go. Additional space. Quick save. Clear the scene. Run. Oh, are you kidding me? Okay. Transperform. That's obviously wrong. Quick save. Clear the scene. Run. Hooray! Woo! Here we go. Right, so now there we are. There's our double bond on the oxygen. So now what we've done is created 2 cylinders. If I go to my numpad and I hit full stop, I'll zoom in on it. There we are. So we've created 2 cylinders and we've offset them from each other so that that now looks like a double bond. So we now have our correct molecule. Let me go back to the viewer window. So here we have the correct molecule. We have the correct atom sizes, we have a material assigned to each element, we have the bonds between each atom. The only thing now that's missing is we don't have a material for the bonds. So for this, we're going to use exactly the same script that we used before, but just modified for bonds. So at the very start of this, we're going to say if not bond in BPY data materials keys, BPY data materials new bond. So what that's saying is we're checking to see whether there's a material in the materials list called bond, and if there isn't one, then we'll generate a new material called bond. And then when we actually create our cylinder objects in this little shading part, we will add our material. So we'll say BPY context active object data materials append BPY data materials bond. Okay, so that will assign the bond material to the bond that we've just created. Okay, and also it would be useful to name these objects as bonds rather than cylinder. Okay, so in order to name the bond, we use the same code from above. So BPY context object name equals bond. Clear the scene, run, and there we go. Okay, so now let's go back to the normal view in the layout tab here, and we see we've got all of our bonds, all of our carbon, hydrogen, oxygen, and phosphorus atoms listed. Okay, so if we want to make this look like a nice object, all we have to do now is edit these materials to look nice. So we're going to go to the properties menu here. Let's take the bond material and just make it completely black. Okay, and now we can look at the hydrogen atoms and we can convert this. A useful thing that you can do is you can look at this drop down menu and you can switch between different materials. However, okay, so now we can look at the hydrogen atoms. Let's color those sort of white metallic color. So if you go to this properties tab, you can click on use nodes, and then rather than just having this standard diffuse material, you can enter different materials. So we could put in a glassy material, we could put in a glowing material, anything that we like, which I sort of covered in some detail previously. But for now, we're going to use the principled BSDF, which is the sort of standard node shader. So we're going to make our hydrogen atom a kind of white metallic color. If you want to see how it looks, you can click the preview drop down. So move that white bar. If we click on base color, we get a color wheel. You can move that right up to the top so it's white rather than gray. And then go to this metallic slider and increase that to max. And then take the roughness and just drop that down to like 0.25-ish. Okay. Right, so that's our hydrogen material. You'll notice it hasn't updated here. Okay, that's because if you look, we're still in viewport shading solid mode. Okay, so this is just like a really loose representation of what we're going to get. And this doesn't show shaders, it just shows diffuse materials. So in order to see what this material really looks like, we have to switch into the render preview, which we do by clicking on the rightmost sphere here at the top. If we do that, you'll notice that everything looks very washed out and dark. That's because we don't have any light sources in the scene right now, so we're not going to do that yet. We'll do that in a second. Okay, what other elements have we got? So we've done hydrogen. What about carbon? Well, call me old-fashioned, but I like carbon to be a dark color. So let's click on Use Nodes again to insert a principled BSDF default shader. Go to the base color, make this black, and then take that metallic and turn it up. I don't know, well, it's how much you like, isn't it? I like it to be not quite fully metallic. And then turn the roughness down a bit so it goes kind of shiny. There we go, that's good. What else have we got? Carbon, hydrogen, oxygen. Oxygen is typically depicted as red in ball and stick diagrams. So let's, again, add a BSDF shader by clicking on Use Nodes. Base color, put that to red. And we can make it a bit metallic again. And again, adjust the roughness. That's good, I like that. And finally, phosphorus. I think phosphorus is usually orange in most ball and stick diagrams that I've seen, so we can color that orange. I might just leave that as the diffuse shader. I quite like the kind of plasticky orange look. You could make it metallic if you like, up to you. Okay, so now we have all the colors for our materials correct. So let's go into the shader mode, which we do by going to this top right menu and clicking on the rightmost sphere to go into render preview. So now we can see those colors we selected have been applied, but it's in the dark. So let's add a light source. So click in the 3D viewport here, hit, so click Shift A to go to the add menu, go down to light, select sun. Okay, that's going to add a sun-like light source. And if you remember from last time, a sun-like light source is a completely uniform collimated light source. Okay, so the light goes from it's isotropic through the entire scene, and its direction is determined by this little handle here, so we can switch the direction of the light. So just raise that up out the way so it's not in the middle of our objects, and then just adjust this angle so that it looks nice. And then if in your hierarchy you select sun, you can get to the light properties menu, which is denoted by this little light bulb. And here in strength, you can turn this up so we can say 10. Great, now that's applying plenty of light. And now we can see our nice metallic hydrogen atoms and the color scheme and the shadows and the smooth shading, and it all looks super nice. But of course, we're still looking at this in Eevee. If you remember from last time, in this properties menu, if we go to this camera icon, we can get to the render properties, and then we can change the rendering engine. So let's change that from Eevee to cycles. Okay, now we're getting the proper ray tracing engine, and we can see these materials in all their glory. We have noise. Okay, so we probably want to add a noise filter. So for noise filtering, in the render properties menu, go to denoising, open that and click the two tick boxes for render and viewport. Remember that there'll be some lag because you have to import the denoising engine, and you can turn both of these to optics, which is what I prefer. And then it should apply some denoising, although it's not doing it very well. Still getting tons of noise around here. Wonder why. It's probably just that I don't have enough render cycles, I imagine. Oh, it's also because I'm using CPU shading. So if you have a good GPU, turn this from CPU to GPU compute, and it'll look much better. Okay, so this is our deoxyribose molecule. One last thing to do before you finish is to turn this from a collection of objects in space into a single object. So if I wanted to move this molecule around and I click on something in it and I press G, which is the movement shortcut, I move this individual atom on its own. I have proportional editing on, which you won't, but I'll move this atom on its own. It's dissociated from everything else. I don't want that. I want this to be a single molecule. Now I could just convert this into a single object, but then I'd lose all of the distinction between the individual atoms, and I kind of want to keep that until I'm perfectly happy with this molecule. Okay, so in the 3D viewport, just draw a rectangle around the molecule, and that will select all of the objects in this molecule. You'll probably end up selecting the light object as well. scroll down to where it says sun, and then control click on the sun. That will deselect it. Okay, and now shift click on the phosphorus atom. That makes the phosphorus atom active. You can see that because it's outlined in yellow rather than orange. And now press P. Now press Control P, and you see you get a context menu that says Set Parent Object to. And if we hit Object, then all of these atoms end up childed to the phosphorus atom. So this phosphorus atom is now the center of our molecule. You can see there are all these dotted lines which denote links between the atoms and this atom. So now if I select the phosphorus atom and I hit G, I can move the whole molecule around as a single object. I can rotate it as a single object, and all the relative positions stay the same. Okay, right. So, we've now generated our deoxyribose molecule. That's enough for this one. Next time, we're going to be importing the rest of the molecules that we need to actually create the DNA and stitching them together and putting them into an array so that they actually build the DNA molecule. So it won't be as long between this tutorial and the next one, I hope. So stay tuned. Thank you very much.